In this example, I will demonstrate how to plan a HAWC plus polarization observation. The tutorial will cover observing time estimates and how to specify those observing details which are required during phase 1 of the SOFIA proposal process in HAWC. HAWC is a SOFIA proposal tool which you will need to use to submit your proposal and the observing details. As target for this exercise, I selected the H2 region W3OH. Note that here in the background we'll see W3 main, one of the first observations of HAWC+. Always start your observing planning with getting flux estimates. State your sources or assumptions for your flux estimates clearly in your technical feasibility section in your proposal. For example, you can get flux estimates from the Herschel archive or Herschel catalogs at IRSA, which are useful for Frankfurt observations. Possible are also KO, ISO observations, and so forth. Or use literature as source for your reference flux. Here, a Herschel paper on W3 unfortunately does not quote flux values. So I already downloaded and cropped 3 Herschel images from the archive. Let's inspect them using HAWC. You of course can use your favorite FITS viewer. Here I have started HAWC. On the first page you enter just the regular proposal information, but now we want to use it actually as FITS viewer. Here in the image menu, go to FITS file image, load your, for example here, the Spire image of W3OH, which I downloaded and cropped already. I like to display it in a log scale because it has a very high dynamical range. All the values, make it a bit colorful, and here it is. And here, this is W3OH. I already loaded, to save time for this video tutorial, 3 other wavelengths, PAX 70 and PAX 160 microns. Spire is at 250 microns. And now we can inspect the data. Here in the upper left you see the values and the pixel size is also given here. This Spire map is calibrated in megajansky per steradian, and when we kind of look here, the peak is at around 100,000 megajansky per steradian. The outskirts, of course depending on how far we want to go out, is around 1000 mega per steradian. Similarly here, the PAX image, which is saturated in the center, peaks around 100 Jansky per pixel, and the outskirts have a few Jansky per pixel. The 70 micron map, also saturated in the center, has similar values. Now, of course, for the Jansky per pixel map, you also need to note the pixel size, which is 3.2 arc seconds. Now I transferred this information here to my script. Herschel 70 micron unit is Jansky per pixel with the noted pixel size. In the outskirts we find around 3 Jansky per pixel. For sight, as you will see, we need the unit Jansky per square arc second. So since the pixel size is about 10 square arc seconds, we have 0.3 Jansky per square arc second in the outskirts at 70 and also at 160 microns. Now Herschel 250 micron map, that was Spire. Unit was megajansky per steradian. In the outskirts, around 1000 mega per steradian. That translates to 0.024 Jansky per square arc seconds. And these are the numbers that we will need for our time estimate. Now, for the time estimate, you can use SITE, the SOFIA Integration Time Estimator. You find it here on our DCS webpage. It defaults to forecast, but let's switch to HAWC+. Obviously, we need to select the HAWC filter. Since we want to do polarization, we use here the filter sections down below, where HWP stands for half wave plate. Let's start with the shortest wavelength, 53 microns. We want to estimate the total integration time to achieve a signal-to-noise ratio of, yeah, well, how much? So on my script here, kind of I made the following assumptions. We saw from the map, let's go down to a level of 0.3 Jansky per square arc seconds. We have to assume some kind of polarization. Let's say we expect a polarization of 5%, which we want to detect at a signal-to-noise of 5. Let's enter this. Signal-to-noise of 5. We have an extended source. We expect 0.3 Jansky per square arc second. That's the flux we want to detect at 5 sigma. The polarization of 5%. And down here you can specify atmospheric conditions, observing circumstances like elevation angle and altitude, corresponding water vapor. Leave it at the default values. That is then, yeah, everybody, that's recommended and everybody does that, so that gives you a reasonable result. Oops, sorry. Calculate. And here we calculate that this observation needs 427 seconds. Now for another filter, you just select another filter. For example, let's go to the longest wavelength E. There we calculated estimate 0.003, or I kind of took that from 0.24, just to kind of rounding not quite correctly actually. 127 seconds. You will see that detail is in this case not very important. The exact timing. Here I calculated also the other times. We get to these numbers: 427 seconds, 353 seconds, 34 seconds, and 127 seconds for all of these different bands, making these assumptions for the different fluxes. Now I should point out that if you want to estimate the magnetic field strength from the polarization via the Chandrasekhar-Fermi method, where you look at the variation in the position angle of the magnetic field, you need a high accuracy in the position angle, and that translates to a high signal-to-noise in the detected polarization. You need at least a signal-to-noise of 8 to employ the Chandrasekhar-Fermi method. So in your feasibility section, explain clearly also your requirements for signal-to-noise for the flux estimates. And now we have all the entries that we need for phase 1. Now, before I go into these details here, let's have a look at an AOR for HAWC+. So you start entering observations by adding an AOR with this button here. Of course, we want to do in this example an HAWC+ polarization observation. Note that we only need to enter entries where there is a red star in phase 1. Once your proposal is accepted, in phase 2, together with the instrument scientist, you go over all the other details. I can't enter a total exposure time here. What I can manipulate is the time per full knot pattern, ABBA, and we leave that at the default of 40 seconds. So the only thing that I can specify here are the AOR repeats. Oops, first I need a target. The target is W3. We can resolve it by SIMPAD, resolve the name. Note that I kind of found out that SIMPAD resolved W3 actually to W3OH. Make sure that SIMPAD or NED does what you want. Otherwise, you can also enter your coordinates manually. And I just plotted apply, because this number comes with a default value which does not necessarily reflect the default entries. So with one AOR repeat and 40 seconds per knot pattern, you get a total exposure time of 320 seconds. Let me explain how this comes. At a full knot pattern of 40 seconds, you do ABBA, meaning bay is the off source, so you're spending actually only 20 seconds on source. But these 20 seconds get multiplied with the dither positions, minimum 4, and for polarimetry with the 4 polarization angles. Thus, you get a minimum total exposure time on source, either 80 seconds for total intensity, but here we selected the polarimetry observation, so that is actually 320 seconds. And now, if you recall, for band A, 53 micron, we need 427 seconds, so a bit more. Thus, we do 2 repeats of the AOR. You could also increase the number of dither points in your pattern, but that increases the length of the AOR. It's preferred to do AOR repeats rather than increase the dither pattern, so that you can have several shorter AORs to do calibration measurements in between. But the main point is entering the total exposure time. Now after I entered 2, I get to the 640 arc seconds total exposure time, which is sufficient. And of course we have to select here the passband. So at this point we are basically done with entering this particular AOR. I recommend that for your own orientation, give it a nice name up here. So that you don't get confused with your several AORs which you might have. I always recommend that you visualize your AOR by taking an image, for example the ones that we already downloaded, and plot the AOR with this button, or here in the overlays with current AOR on top of your map. Now this is the field of HAWC for the shortest wavelength filter, 53 microns, plus 4 dither positions. You see the 4 dither positions. So the inner part here is nicely covered, and we see at the outskirts we get the 3 Jansky per pixel that we started with. Of course that was planned like that. If we zoom out a bit, you also see the off positions with the current settings of the knot and chop parameters. Let's bring these up again. Here we have a chop throw of 300 arc seconds by default with a certain position angle. These parameters don't need to be specified right now. As you can see, they don't have red stars. And the details here will be fixed together with the instrument scientist during phase 2. However, you need to kind of convince yourself that your observations are possible with, for example, not matched chop at a certain chop throw and angle. Now, if we look, for example, at a longer wavelength, switching to the Spire image, though of course this flux is rather low, but we're getting into the 1000 megajansky per sterradian in this area, which was our target flux. So we might want to kind of rotate that a little bit, at least to make sure, yes, it is possible, and actually increase the chop throw. If you try 600, you will see that is too much, so HAWC warns you about ranges for valid input ranges. 500 arc seconds chop throw. Let's turn that a little bit over and Zoom out. Now this looks like relatively clear positions, and so that works. Another thing I want to demonstrate here is your example rotation angle. Note that HAWC Plus doesn't have a beam rotator, and it cannot predict which position angle the footprint of the array has on the sky. Here you can just play around with a few examples to see. Let me zoom in again. I can center the source with this, but it is already centered. Now let me center again. You see how the different design pattern looks relatively different when you have different angles. Now just some more examples. So you get some of a configuration like this. Essentially that means you only get the inner part fully covered. You don't know where the position angle of this is, so you can't plan for getting this extent in this direction and only this extent in the other direction. Detailed planning, but as I said, will be done together with the instrument scientist in phase 2. So far so good. Now we have these parameters set, at least at reasonable values. Go back to observations. Now we want to do several filters. So let's duplicate the AOR with this button, for example. And by just changing the filter to, for example, C, that is W3OH band C. Now, of course, check the time. This time needed only, the time here was less than 320 seconds, as we see here. Oh, no, it was 353 seconds. So leave it at a repeat of 2. And done. Next one. This will be, come on, W3OH band D. And here we only need 34 seconds, so the 320 will be plenty. And apply that. And now we come to band E, give it a nice name. Oops. And for band E, we wanted to have 127 seconds, so 1 repeat is sufficient. And now we see here our exposure times as planned. The total durations add up here, and this adds up to a total duration, these 4 filters, of 108 minutes. You can see a bit more detailed about the observing time calculation here, where it gives you exactly how much the overhead is, and the exposure time, and the total of the duration. Now let's see how this actually looks when we now visualize all of the AORs. All AORs, yes. Now we see all the different AORs, all the different field of views or array sizes of HAWC. I can switch on and off separate ones here, so that kind of gives a better view. This is the smallest one, where we can see, we still get the center part. When we go to the longer bands, the field of view gets larger and larger and larger. but even for this large one, we see we have good chop image. I should look at that in the Spire map, of course, because that is the long wavelength map. Well, maybe we need to push that a little bit to the left, or kind of maybe go here and then have another image here. Have a larger Spire map to evaluate that, but these are details that are fixed in phase 2, but this looks like compact enough so that we can do a chop knot configuration. If you have any questions, if something is feasible or not, send us an email here to our help desk email. Just to summarize what we just entered into the phase 1 AORs, reminder, only the entries with the stars are required. All the others will be detailed together with the instrument scientist during phase 2. You had to figure out how to break up the total integration time into repeats and knot patterns. Keep the time per full knot pattern at 40 seconds, which gives you a total integration time of 20 on source and 20 off source. Now, these 20 seconds get multiplied with the dither positions and for polarimetry with 4 polarizer angles. Therefore, you have the minimum total exposure time of 80 seconds for total intensity, or, as in here in this example, 320 seconds for polarimetry. If you need more time, increase the AOR repeats rather than adding dither positions. That is because between AORs, internal calibration is possible, thus improving the accuracy. If you increase the length of an AOR by adding more dither points, you have less internal calibration possibilities. Thank you very much for watching this video tutorial.